So by means of short introduction, Christopher has over 20 years of experience in offshore engineering, and his current role is engineering director at Peritus International, a specialist subsea engineering consultancy. He has extensive knowledge of various finite element packages, including ANSYS, Abacus, Autopipe, SolidWorks, Offpipe, and Sage, and has led a large number of subsea cable and pipeline projects in some of the most hostile environments in the world. So, Chris, over to you. Yeah. Go ahead. If you could share your presentation, maybe, then we'll be able to see it.
Oh, I thought you could. Okay, hold on a second.
Yeah, it's at the bottom of the screen. You'd have exactly perfect. Good. Then over to you. I'll now stay quiet.
Yeah. Hi everybody. Last presentation of the day, so hopefully there won't be too many questions. I'm sure you've all had a good day or two of this. So yeah, I shall get on with it as quickly as I can. Please work. There we go. So I will give a little bit of information about Peritus and then talk through some of the more traditional approaches to cable stability and what we kind of have been doing in the past versus some of the things that we've been looking into and getting involved with in the last couple of years, which is really pushing the boundaries forward and really focusing on what we can do for cables as opposed to kind of the historical approaches which have been very much aimed at pipelines, whereas it suits the pipeline, it doesn't really suit a cable. The size difference and everything else is huge. How they respond is very different. So there's definitely a lot of work and a lot of good things that we can do to improve things from a cable point of view. Peritus was formed in 2010, so we've been around for about 12 years now. We were formed by a whole pile of guys who really enjoy the technical, challenging side of oil and gas to start with, and wanted to maintain a fairly small niche company in terms of what kind of projects and challenging work we would do. We weren't interested in just being a large sort of handle turner kind of project thing. But so we really focus on some of the more interesting things. We've been involved in lots of different wind and wave and so cable projects, looking at various aspects of offshore kind of renewables, etc. the last couple of years. And because we come from a pipeline point of view, we have focused a fair bit more maybe on the cable side of it. We found that's an area where our skill set really suits us. One of the key things we've also with Peritus is we're 11 years with no lost time incidents, so really good safety record, and that's something we really want to sort of maintain and keep going. So on to cable stability. I'm sure a lot of you, probably if you've looked through sort of classic literature, will have seen something like this. This is obviously a pipeline. What we would tend to do is put concrete on it to try and keep it stable. And obviously we're looking at how the wave and the current would sort of cause the pipeline to move around. And then realistically, the only real resistance we had was a sort of a very simple soils approach and a pipeline weight. And that would be the kind of what we would do for a pipeline. And I think it's a good starting point to kind of highlight that, a small pipeline is probably 5 to 6 inches. So 15 centimeters would be, the starting point for what we would be interested in here, up to 1 meter. And a lot of the research and development that was originally done is on pipelines sort of 24 inches, about that kind of size, bigger than 16 inches as a minimum, because basically if it was less than 16 inches, we always buried it. So we kind of, as an initial starting point, just kind of ignored a lot of that and focused on the larger stuff that was always on the seabed. So that kind of starts to give you an idea of the big difference, is that we're looking at something that, so 16 inches straight off is already sort of 40 centimeters bigger in diameter. So it's a different mindset when we're looking at a cable to when we're looking at a sort of a pipeline. One of the more traditional things that as the industry moved forward, as we moved into looking at embedment. So this is a way of us trying to increasing the sort of how much resistance we get in the seabed from a sort of very simple starting point approach. And so on clays and sands, we found that initially when we started looking into this, that there's two main factors kind of impact how much embedment we could predict for a pipeline to keep it stable. And we sort of started off with the conventional approach that we would use for a pipeline, and a pipeline is very rigid. And so typically we get sort of a dynamic amplification factor on the lay process of about 1.5 kind of thing. So basically that's like, imagine as a simple thing, you have your weight associated with your pipeline, and as it's touching down the seabed and you're taking into account the vessel motions, etc., you can start to increase the kind of the weight effect by about 1.5 to give you the kind of equivalent embedment of what we were seeing from a pipeline point of view. So we've done some analysis looking at that moving forward, trying to say what would happen if we looked at a cable and do a similar kind of analysis with a cable. So we sort of built an couple of Orcaflex models where we do some very simple static type analysis, just looking at it, adding in the catenary effects, and then into sort of quasi-static analysis, and then onto full dynamic where we include the vessel motion and look at different sea states, etc., that we would be able to work in. In doing that, we started off with quite a small cable, and it was quite interesting. We could, when we did a static kind of approach, we very much matched what kind of embedment factors, etc., we would anticipate compared to a pipeline. But when we started looking more at the sort of dynamic effects, we started to see a huge difference in the two different processes. The cables, we were getting much larger kind of embedment effects happening. So a factor of 5 or 6 on a kind of smaller cable. And then when we went to a slightly larger cable, the dynamic effects became much more significant. And that has a huge impact when we sort of compare everything else. You're certainly looking at nearly up to 3,000% increase in what we're kind of looking at in terms of an embedment of something and how it behaves. And then that in turn, if we go a step back, it kind of changes what your stability would be then for the cable. So if we, for example, we went with a static approach for a small cable, we could say that we would be allowed to lay the cable and it would be stable in 2.2 meter seas, sort of sea state. So that typically, say we were working in the North Sea, would probably limit us to about a 2-3 month weather window of trying to install a cable. And then by going to full dynamic analysis and doing everything else, we found that we could actually, the cable then remains stable for up to a 5 meter sea state, which basically then allows us to extend that period where we can leave the cable exposed on the seabed to basically 9 months or something equivalent for that. And it was a similar kind of effect we saw with the larger cable as well, which is a significant gain because it means that you're not tied in to, if you're using the conventional approach of having to lay a cable and basically straight away trench it. You've allowed yourself a window where you can lay all your inter-array cables and then sort of plan your trenching campaign to work with that so that you can basically extend it from a 1 month or 2 month kind of very tight schedule to allowing yourselves 4, 5, 6 months to be able to fit it all in to go with everything. So that was one of the first big kind of factors we looked at and found a significant benefit in there, is looking at how much embedment we can actually associate with a cable versus with the pipeline in terms of that. And we've actually recently been taking this a little bit further. Very recently, I don't have any results to kind of follow that up yet, but the cable is much smaller, obviously, and the amount of embedment it sees. Say if you take a 100 mil diameter cable, and you've only got 10% embedment. So you'd only 10 millimeters embedment. So that's very small, and you wouldn't be able to pick that up with a typical survey. However, that's probably a fairly large amount of embedment for a cable. When we look at a pipeline and you have a 500 mil pipe sitting there, and it's only got, again, 10 mil embedment, you wouldn't even see it. So we wouldn't have recorded zero embedment for a pipeline, whereas actually, in this case, from a cable's point of view, it's a significant amount of embedment. And so that top layer of soil and how that top layer of soil reacts and behaves is really important for a cable. So again, that's the latest bit we're sort of learning and working on now, is furthering. We've understood the kind of dynamic effects now, and now we're looking at the soils again from a cable point of view to actually properly get a better feel for the levels of embedment we're seeing. And that embedment makes such a big difference to the weather window you can leave your cable on the seabed for. Moving on, and now unfortunately we have no embedment because we've other areas we've been looking at is kind of rocky seabeds. This is an area where Chaz has been part of the JIP and working on preparing the British standard for cables stability on a rocky seabed. Peritus, along with Aurora and University of Western Australia and University of Southampton, have really been looking at kind of some of the parameters that affect this, and using some of the knowledge and things we've gained as well from some of the sort of current software we have available to us to actually understand and work with that to try and look at what happens for a cable on a rocky seabed where we don't get any embedment. But again, we would expect, how does a cable behave to a pipeline? So it's very different from a lot of reasons. One, this shows you a couple of things of a project we worked on fairly recently. And it's a very rocky seabed, so no real embedment. But what we then get is lots of free spans happening, so that the cable is very rarely in contact with the seabed. We have what we call high gappiness. Basically, there's lots of gaps underneath the cable, which then in turn means that there's a lot of flow allowed around the cable. So you're not like a conventional pipeline approach where you basically assume these gaps are very small in relation to the diameter of the pipe. Here, the gaps are very large in comparison to the diameter of the cable. So it makes a big difference. Obviously, we still don't have much. If we were to take a flat rocky surface, we don't have much friction there between the rock and the cable. However, when you actually allow for the really rough nature of most seabeds when in comparison to a cable size, you actually do have a much higher kind of friction effect there. The rocks are a lot rougher for a cable than they would be for a pipeline. So all of that kind of goes to building a slightly different approach to how we should address a cable sitting on a rocky seabed to a pipeline being on a rocky seabed. Here we moved on one step further. So we looked and learned a lot about the kind of interaction between the cable and the seabed, and then we wanted to understand the full 3D effect of that sort of cable, how it behaves. So here we're going from one wind turbine to another, and we have a whole cable route in there. We're laying the cable along a certain sort of route, and then we're applying a full sort of storm analysis on it to understand what's really happening. The other thing we also looked at is the tension in the cable. If you increase the tension, you get more gaps. How does that behave? What does that change in the system? So you can see in here the difference between the red line, where basically the cable is always free spanning, just about. It just touches down on the rocks, and the blue line where it's allowed to sag a bit more and touch down. So what we found is that by doing the analysis, the cables move around a fair bit. But what they do then is they start kind of wrapping themselves around features. They find things to attach themselves to. So, for example, from the analysis we did, we found the cables were moving 3.5 meters, but then they were locking up and getting into a much more sort of static position because they've actually found a feature to wrap themselves around. So they become stable, they don't really follow, again, what we would call the classic pipeline approach, where we're trying to work to 10D. Here we're actually allowing it to move, 100D or something like that, but then it is stable once it reaches that point. We're able to then check by doing the full analysis that the system we're not overstressing the cables, there's no real problems. And one of the other more interesting bits is we're then also finding that the cable then gets stuck into nooks and crannies. So we don't have the kind of situation whereby we'll get a lot of fatigue, because the fatigue is really locked in. It's not moving anywhere. This sort of shows you a good example of that, where you can see the cables eventually found itself sitting in a really deep kind of gully here, and it's just locked into that position. On this side here, this is actually us looking at the whole analysis and seeing how the cable moves, and the different bits of the cable move at different rates, depending on how the storm analysis is going through. But again, what we found is we'd run this once and the cable would move. We'd run it again and the cable might move a little bit more. But then after that, the cable stops moving and it locks into a position. And then we don't see anything else happening. Then to kind of back it all up, there was a couple of cables in the field that we were looking at that were installed, and they were surveyed over a period of time with some various storms. So the green arrows mark where there were surveys done, and then the orange arrows mark where there were storms that came through, and so they were able to actually look at this and understand what happened. Here you can see the results of that. What it shows is that the cable moves quite significantly, 3.5 to 4 meters in some cases, off the original center line. And then with time, though, and more storms, it basically just settles down and locks itself in. And then once it's in that situation, it's stable. It doesn't move anymore. So that was another great thing, and we were in charge of reviewing this work. Aurora did a lot of the sort of actual more complex stuff. We did the finite element analysis to kind of verify the design and things. And overall, in total, between us, the analysis went from, I think, 600 kind of bags of rock that had to be installed to mitigate the movement, down to some sort of order of, I think, 30. So it's a huge saving in terms of how much mitigation was required for the project. In conclusion, really, this is where we are at the moment, and it's obviously an area where we're constantly trying to improve. Peritus were part of the original DMV JIP pills, which was to look at stability, and the idea was to move more into cables as well. And we've learned an awful lot from that first JIP, and there is a second JIP being prepared at the moment to further that. And again, we're aiming to be part of that, really focus on improving these sort of things. And really, as the first JIP, we did a lot of the pipe-style interaction kind of part of that. So that's another area where we're focusing on here, which is one of the reasons for a lot of this work we've worked on here. So the conclusions really is that, if you can understand the embedment, having a significant amount of embedment. So, and that's just learning and understanding what the kind of soils are and how soils behave with a cable versus a pipeline can have a significant impact on the cable stability. If we go ahead and look at doing some dynamic analysis on that kind of cable installation, again, it significantly helps with that stability, which then gives the cable installers and operators a much longer window to be able to do things, which results in a huge cost saving. Then again, when we come to, so as I said, existing design codes inherently conservative and a bit misleading for cables. And that follows both from a stability and an embedment point of view. So both of those areas, there's a huge amount of gain for us in terms of doing that. And being able to model it all and look at it all in a huge amount more detail means that we can basically significantly reduce costs and risk for the clients. Okay, hopefully, I think that's me just about on time, and that's me finished. Thank you.
Thank you. Okay, Chris, we have a little bit of time left. Maybe I'll start off with the first question. If you could go back to slide 15, because I heard some gasps in the audience when you showed slide 15.
Which is 15, that one there.
Yes. Can you tell us if the z-axis has been exaggerated a little bit, or if that's what it really looks like?
Quite significantly. I mean, the thing you've got to remember here is that a cable obviously is, I mean, and what you're looking at there is just the blue and the red are the bottom of the cable. Unfortunately, with the kind of software we're using, where we exaggerate the scale so that we can actually see how gappy the pipe is and things like that, if we try and put a cable in, what we end up with is a cable that's nearly the same size as the sort of gappiness and the features around it. So yeah, this is just the cable at the bottom of the cable that you're able to see interacting with the seabed. So, and it is exaggerated. To be honest, on here, I think the exaggeration is probably about 10, between 5 and 10, kind of on the thing, to give you an idea. It's mainly just to show and highlight that there is a big difference, and by having more tension, we actually have more gappiness, which actually helps us because it allows more flow either side of the cable, which then reduces the kind of forces on the cable.
Yeah. Okay, perfect. But I hope that puts it a little bit in perspective. But of course, then it shows the gaps better. Yeah. Do we have any questions from the audience? So I'll ask more. If no one wants to ask, then I'll ask one more. So in the conclusions, you say that the engineering saves costs and reduces risks. And I like to go back in time to the first HVDC project NKT has ever done in 1953, where a cable was laid basically of some ship by hand, and that operated well until the 70s, when the capacity of the cable was increased by 50%, and so was the voltage, and then it worked for another 15 years without any issues. So I'm wondering how much deeper do we go in the analysis, and how much more can we gain with incremental changes that we cannot achieve with safety factors or just empirical trials?
I think there's two bits to kind of an approach like that. The kind of cable you're talking about, that their approach was, we'll probably over-design it, we'll throw it in, knowing we've over-designed it, and we'll see what happens to it. We'll wait and see, kind of thing. And if it don't break, try a bit harder, kind of thing to it. That's great. What we tend to find now is that the first approach is, what's the absolute minimum cost I can do with my cable? So nothing is over-designed anymore. Everything is designed to an exact end of life period. We'll design everything for 20 to 25, maybe 50 years, but that's right at the very limit. Nothing was designed to last 200 years or anything. So there's a lot to go into saying that we use a risk-based approach in this approach now. So we have reduced a lot that kind of excess capacity in the system. So that's one of the reasons why some people will say, hey, we're reinventing the wheel by wanting to do additional engineering. We're doing additional engineering to further reduce the costs and to further benefit the client. So the client maybe in the old days might have said, okay, we've 50% over designed a cable and the cost of this, whereas now they're going, hey, we've 10% under designed the cable, but we've saved 50% in the cost. And so if we're able to then go, okay, we can actually now improve things again further, but we are still working to a 20-year or 50-year design life. We're not now suddenly being able to extend that design life again, past beyond. That's still a learning curve that we're going through with this sort of work. So yeah, it's all about, I think, cost reduction and cost saving these days versus the risk level. Whereas I think, as you say, a 30-year ago, we were a lot more belt and braces in how we designed something. Yeah.
Okay. And at what point do you reconnect this modeling to actual empirical data, because I myself remember as an engineer, I also did modeling of heat exchangers, but the actual empirical data I was basing my models on was from the 50s and 60s, because that was the only trials that were available. And we were all aware that computational fluid dynamics was not nearly accurate enough to truly model every effect that the empirical data would suggest.
Yeah, I would agree. So as part of the work we did do here, and that was done on for one of these projects, there were 2 trial cables put in, and then we were able to kind of understand and compare what the theory said versus what happened with the storms and these 2 trial cables. And the results were really good, really promising, and we were able to kind of match very well what happened in reality with what kind of was predicted. So there's a nice bit there. I think with a lot of it, the cable approach and you say fluid dynamics and things like that, it's always a tricky one. It's only ever as good as what you want to put in and how you want to sort of edit it. We've spent a lot of time on the bits we understand. And a lot of my experience and the kind of guys is on a pipeline. So we're very good at how we model pipe soil interaction. That's been something that we've done for years and understood for years. So when we go from a pipe soil interaction down to now a cable soil interaction, we are trying to learn, and we're basing it on what we know from the pipe, but then also what we're learning from in-field and talking to the installers and the operators. So yeah, it's all a learning curve. I think the good news is it's going to be a learning curve for a long time. Hopefully I'll have a lot more grey hair before I can ever get to the point where I'm sort of saying, there's no more analysis we can do on this.
Yeah. Okay, great. Then one last chance to ask questions? No? Okay. But then in that case, Chris, thank you very much for taking the Grave Night shift. It's was a great final to the conference. So I'll say now a few words to close off, and we can then all enjoy some last chances for networking.